Welcome in everyone. In this video, I'm going to go over inverse functions. The first thing I'm going to do is explain what are inverse functions. Then I'm going to go over the graphs of inverse functions, namely how to find the inverse of a graph and how to tell if two different graphs are inverses of one another. From there, I'll move on to actual function equations and the same process, how to find the inverse of a function equation and how to tell whether two function equations are inverses. Let's get into it. So what are inverse functions? Well, in order to get a deeper understanding, I want to go back to what inverse operations are. And more specifically even, inverse operations with the same values. So for example, you all understand that addition and subtraction are inverse operations, multiplication and division are inverse operations, squaring and square rooting are inverse operations, so on, so on, so on. But with the same value, maybe I say something as a teacher or professor, I'll add 5 points to your test score, but then I'll take 5 points away from your test score. I completely undid what I added to your test score. So inverse operations. Inverse functions are like this, except they are entire functions that undo each other. And those functions, as you have seen up until this point in your mathematical career, can involve adding, subtracting, multiplying, dividing, squaring, square rooting, other exponents as well. All at once in combination with one another. So we can't just say that, oh yeah, addition and subtraction are inverses. We will have entire functions with multiple of these operations happening that undo each other. And the other thing about inverse functions is that when you have a function and its inverse, they both must be functions. And this can lead to some domain shenanigans, but we'll get to that when we need to get to that. Lest I forget, the most important idea to be successful with inverse functions is that you are swapping x and y. If you can remember this will save you a lot of time and anxiety when working with inverse functions. Finding the inverse of a graph. So here on the left coordinate plane, you can see that I have a function f of x, and yes, it is a function because it passes the vertical line test. And this function has this domain from -8 to 9, and this range from -7 to 8. Now, it would be a real shame if we tried to find the inverse of this, plotted it over here, and the inverse was not a function. It would have wasted all of that work. So what I'm going to do instead is first check to see whether or not the inverse will be a function. And you can do that by using the horizontal line test. The horizontal line test is almost identical to the vertical line test, just with horizontal lines, and it will tell you whether or not the inverse will be a function. So if you look at this graph and you pass horizontal lines through it, all the horizontal lines will only touch the graph once, which means the inverse will be a function. So we can proceed with finding the inverse graph of this function. So when you do that, what I like to do is, if you're given a graph, or maybe you have to graph it first, is find the nice coordinates here, or the nice points with whole number coordinates, and just list those out left to right, like this. And from here, all you have to do is remember that big idea from the last slide in swapping the x's and y's. So this first point would become 8, -8. The second point would become 7, -2. And I want to make sure here you understand I'm not swapping signs, I'm just swapping the positions of these numbers. And so you'll do that for the rest of the points. And then I will plot these points again from left to right, and then I will connect them as I go. So 8, -8 is right here. Oops. There we go. 7, -2 is right here. 4, 1 is right here. -4, 3 is right here. And then -7, 9 is right here. So -8, -8 connects to 7, -2, connects to 4, 1, connects to -4, 3, connects to -7, 9. There we go. And that's what the inverse of this graph looks like. And aside from the horrible drawing of this graph, it is still a function. It passes the vertical line test. Now, one thing I want to point out here is that the domain and range of this new inverse graph are like this. The domain is from -7 to 8, and the range is from -8 to 9. And you can see, maybe from the domain and range up here, is that they just swapped positions, which matches up with the big idea. You just swap all of the x's and all of the y's. So all of the x's of the original function became all of the y's of the inverse. All of the y's of the original function became all of the x's of the inverse. So this idea that all x's swap with all y's plays a really big part in this particular idea, this idea of inverses. And that even extends into why we use the horizontal line test to see if the inverse will be a function. So for example, if I put a horizontal line here through that point on the left graph, I can tell you for certain that that line is y equals 4. But if we invert that, swap out all the x's for y's and all of the y's for x's, and I come over here and draw that same line, it will now be x equals 4, which is a vertical line. So running through horizontal lines on the original function will swap to vertical lines in the inverse function. So we can check even before we start taking the inverse whether or not the inverse exists and whether or not we should proceed with finding the inverse function. And yet another reason to make sure you understand this big idea of swapping x and y is if I graph the original function on the same coordinate plane as the inverse, you can see that there is some kind of symmetry going on here. And the symmetry happens as a reflection over the line y equals x. So here you can see the line y equals x graphed as a dashed line on the coordinate plane, and you can see that the dots, or these points, are being reflected over this line. And that's a really big idea on how you can tell whether or not two functions you're looking at are inverses of each other. The last little bit here that I have to take care of on this slide is the inverse function notation, and it will look a lot like the original function because, again, the inverse and its function are related to one another. But the difference here will be that the inverse function will have a -1 on the f. And this is not meant as a -1 exponent. You would read this f inverse of x. Don't try to put this in the bottom of a fraction or anything like that. This is just f inverse of x. On this slide, we'll find the inverse of another graph. Just to point out, you might be given a function and asked to graph it first, and then find the inverse of that graph. But just to go through the process again, we can start by noticing that this is a function. It passes the vertical line test, but this time if we use the horizontal line test, you'll see that the inverse will not be a function. And generally speaking, you won't be asked to find the inverse if the inverse will not also be a function. So what do we do here? Well, we can notice that this is an increasing part of the parabola, and this is a decreasing part of the parabola. And honestly, we could pick either side of the parabola, either to the left of the vertex or to the right of the vertex. Either side works. So what I think I'll do is I will work with the left side of the parabola. So I'm going to come over here and I'm going to go ahead and erase the right side of this parabola. There we go. Generally what happens is you will not be asked to decide which part of the parabola you'll want to do. You'll know here that x has to be less than or equal to, say, -3. So you would know that already, which means you would just have to graph the left side of this function. All right, so we have the function graphed. What do? We just go through and do the same process as the last slide. Find some nice points from left to right. Swap all the x and y coordinates. Plot these new ordered pairs. And then we just have to make sure we connect them as we see them. So -4, -6 connects to 1, -5, connects to 4, -4, connects to 5, -3. Now we're super close here. You can tell that this graph, let's see, starts at this vertex point, which is here. So this graph should also start at the vertex point, which would correspond to this one. And then it would go forever in the other direction. So we can extend this out like that. And you can further see this if we plot the original function here on this coordinate plane. So here's what that looks like. You can see there the original function and the inverse are reflected over this line, y equals x. And over here, since we did mention that the domain of the original function is less than or equal to -3, in interval notation, that would be this. And you can see even from the graph, -∞ to -3 would be the domain. But the range for this original function would be -∞ to +5. And if you look at the green graph over here, the inverse, you can see that the range and domain changed places because all the x's become y's and all the y's become x's. So it all lines up and we have a very nice inverse relationship here. And from the graphs, we go over into finding the inverse of the function from an equation. So there's a process to this. You will be given a function and be asked to find the inverse. And the first thing you want to do is replace f of x with y. Then you want to swap all y's out for x's and all x's out for y's. That's that big swap idea again. From there, you want to solve for y, and then you want to use the inverse notation at the end. And as I go through examples, I'll explain why you want to use the inverse notation at the end. For the first example here, we're going to find the inverse function for f of x equals 5x plus 4. And generally speaking, you will be given functions that are already one-to-one. So what that means is the first thing we'll do is we'll go ahead and replace the f of x with y, because after all, that is all f of x is doing anyway. It's taking the place of y. From there, I will go ahead and replace all of the y's with x's and all of the x's with y's. Now, this will lead to us using the inverse notation at the end, because when you make this swap, the resulting function will not be 5x plus 4, which is what this y is equal to. This is a new y, because when we solve for it, we're going to get a different function. So from there, all we have to do is solve for y. which involves subtracting 4 from both sides to give us x minus 4 equals 5y. And then lastly, we can divide both sides by 5. And you can do that either by dividing the entire side or each term individually. Either way, you'll end up with y equals x minus 4 all over 5. From there, we will not use the y anymore. We will use the inverse notation because that's just what we've done. We have found the inverse function. And again, you can see that this y equals a different function from this one, so we have to label it something different. So how can you tell that you have done this correctly? Well, one thing you can do is you can compose the function and its inverse to see if you get x. Now, if this statement here is true, then you have found inverses. So I'm going to go ahead and check this one time here. We can take f, which is f, and compose it with f inverse of x. So really what that means is we're going to replace that f inverse of x with the actual function, x minus 4 over 5. And from there, we know we have to substitute this expression into this function. So it'll look something like this. And you can see that the inverse function was substituted into the original function. From there, you can see that the 5's reduce away pretty nicely here. 5 divided by 5 is 1, leaving you with an x minus 4. But then this plus 4 comes along for the ride, and you can see that the 4's reduce, leaving you with just x. Now, when you check normally, you're supposed to check both compositions. And what I mean by that is you find f of f inverse of x, but you should also find f inverse of f of x. It doesn't matter how you compose these functions, you should get x. And it does hold true that if you write the composition out this way, you still get x. So these two functions are in fact inverses of each other, and this is how you can prove it. For this example, we will also find the inverse function, but this time you can see there is a cube root involved. So we have the function f of x equals the cube root of x minus 5, and then outside of the cube root is plus 9. So what we have to do, same process, and I haven't mentioned yet, but I love finding the inverse step because the first two steps literally require absolutely no math. So replace f of x with y, swap out all of the y's for x's, and all of the x's for y's. All right, so we still have a cube root of y minus 5 plus 9. All right, the third step where you solve for y, again, this is a new function because the y is in a different place than what it was up here. We have to solve for y. That's where all the math happens. So we can solve for y pretty easily just by subtracting 9, as we can't do anything with the cube root until it's isolated. So minus 9, that means x minus 9 equals the cube root of y minus 5. From there, we can cube both sides to get rid of the cube root. So we have x minus 9 cubed equals y minus 5. And then from there, of course, we can just add 5 to both sides. Now, when you do this on the left, the 5 is added to the outside. So I'm going to do 2 steps in one. I'm going to go ahead and write down what we have left over here on the right. So we have left x minus 9 cubed plus 5. But also, I'm going to go ahead and use the inverse notation right away. So this will equal f inverse of x. Now for this example, I'm going to go ahead and check both compositions. So the first thing I'm going to do is I'm going to find f of f inverse of x. And basically what you're doing is you're substituting the function f inverse of x in for x in the original function. So it'll look something like this. And just so you can see it again, here is the inverse function substituted in for x in the original function. Cool. So from here, we can do some canceling. You can see that the +5 and the -5 will cancel. All right, that'll leave us with the cube root of x minus 9 cubed plus 9. From here, the cube in the cube root will reduce, leaving us with x minus 9 plus 9, which is just x. So there's one way, so the 9's reduced. Now the other way, if I say f inverse of f of x, that will be this expression on screen. But I promise you it also reduces to x. So I'm going to put an x way down here. But something really interesting happens, and I wanted to take the time to show this to you. The operations will cancel out again all the way. So the first ones that'll cancel here will be the +9 and the -9. So those will reduce, which leaves you with this expression. Then the cube in the cube root will reduce, leaving you with x minus 5 plus 5, and then the -5 and the +5 will reduce to give you x. Why did I bother going over both versions in this example? One, I had enough space. Maybe that's debatable. Anyway, to point out the following. If you look at how the operations, the inverse operations reduced, we had the plus and -5 reduce first, the cube and cube root reduce second, and the plus and -9 reduce last. But when you compose the opposite direction, the operations all reduce in the exact opposite order. So the 9's reduced here first, then the cube and the cube root, and then the 5's. So the order with which you cancel things does matter, but either way you'll end up with x. So if you decide to only use one of these compositions to check whether or not two functions are inverses, that should suffice. Last example, let's go ahead and find that inverse. And just to say it here, I will not be checking to see if they're inverses by composition. That's just going to be too much for this example. So first thing, again, no math. Make the function notation y. Everything else comes along for the ride. All right. Next, all of the y's become x's and all of the x's become y's. And yes, there are two x's over there. So you will have to make each of them y. From here, all of the math happens. Solve for y. How the heck are you supposed to do that? Well, when you're starting out with a rational function with more than one x, you do the first two steps, fine, but then you have to multiply both sides by this denominator. So that will look like 15y minus 23 times x equals 3y minus 1. And still, we cannot solve for y right now. We have to have exactly one y in our equation somewhere in order to solve for it. So I think the next thing we should do here is distribute the x. From here, we can start to see how to get y isolated. And what we'll have to do is we'll have to get all of the terms with y on one side of the equation so we can do some common factoring. But we need all of the terms without y to be on the other side of the equation. And that will look something like this. Now that all of the terms with y are on one side, we can common factor the y out of those terms, leaving us with a 15x minus 3 equaling 23x minus 1. And then the final thing to do here is to divide both sides by 15x minus 3, which will isolate y. So we will have h inverse of x this time because, again, we have to match our letters here. It started with h, we'll have h inverse. That will be equal to 23x minus 1 all over 15x minus 3. And as I mentioned at the beginning of this example, I will not be doing any compositions here to check to make sure that h inverse of x equals x. But you're more than welcome to give it a try. I promise it will. And that's it for this video. I hope this video helps you out. Good luck.